Swayam Prabha. Digital India. Educated India.
We will continue with our discussion on surface tension driven flows. To summarize, we have discussed about various equations that describe the motion of a fluid in a capillary, in a narrow capillary, and we have considered both cases, one with inertial effects and another without inertial effects. So, all those we have discussed, and we have been discussing about certain limitations of the simplified model that we have developed so far. So, we will continue with the limitations of the model. We have discussed about one limitation, and we have introduced the concept of the added mass or the virtual mass. Next, we will discuss about the sanctity of the fully developed velocity profile consideration. So, if you look at this schematic, you will see that first there is an entrance region of length L1 where the flow is hydrodynamically developing. This region may be very short, but it will be present. Then there is a fully developed region which is also the equivalently the Poiseuille flow regime, and then there is a third regime which is normally not encountered in a channel which is entirely filled with the same liquid, but here there is a channel which is partially filled, so that there is a meniscus. Now, the velocity profile at the end close to the meniscus should adjust to the shape of the meniscus, right. You can clearly see that the shape of the meniscus which is here does not conform to a parabolic velocity profile, right. Therefore, there is a third regime which is called as the surface traction regime or meniscus traction regime of length L3, where the fully developed velocity profile gradually adjusts to the shape of the meniscus. Okay. So, to summarize, there are three regimes: entrance regime or the developing regime, the fully developed regime, and the surface traction regime. Now, what regimes will be present? See, it depends on what is the total length of the fluid column. Let us say this total length at some instant, this x is equal to x1. Okay. Now, if x1 is less than L1 plus L3, then the fully developed Poiseuille flow regime will be absent altogether, because you have to remember that there must be a developing region, how small maybe it will be there, and there must be a meniscus traction regime, that is a must, because the velocity profile has to adjust to the shape of the meniscus. So, depending on the instantaneous length, all the three regimes may be present, but at least the entrance regime will be there, and if x is greater than L1 but less than L1 plus L3, then L2 will be 0 and there will be meniscus traction regime, but no Poiseuille flow regime. Now, when we have considered the drag force or the viscous force, there we have only considered the fully developed Poiseuille flow regime for evaluating the drag force in our calculations. But if you take into account the existence of these two additional regimes, then that will alter the drag force calculation. How it will alter the drag force calculation, that cannot be worked out numerically but analytically, but through numerical calculations one can do some curve fitting and say that if dfd star dx be the gradient of the drag force with a star means fully developed, then the actual one is basically a 1 plus a function of x by hydraulic radius, where the function of x by hydraulic radius can be fitted by a polynomial. So, this is basically not a fundamental analytical work. This is what is this? This is basically curve fitting of numerical data. So, doing numerical simulations in the for the cases where all the 3 regimes are present, then that can be suitably normalized in this particular form, where the gradient of axial gradient of drag force is equal to a factor where the factor is greater than 1 times the gradient of the drag force for a fully developed flow. And the question is, how do you calculate the gradient of drag force for a fully developed flow? Let us come to the board and explain that. So, let us say there is a circular capillary of radius r. Now, you take a small control volume of length dx. If the drag force acting on this is dFd, then what is dFd? What is the elemental drag force on this small element? Tau wall into 2 pi r dx. So, this is I mean this dFd, this can be expressed in a general case. So, dFd dx is tau wall into 2 pi r. This is true no matter whether the flow is fully developed, developing, whatever. Now, the calculation of tau wall will depend on what is the velocity profile. So, if it is fully developed, then u by u average is equal to 2 into 1 minus small r square by capital R square. This is fully developed flow of a Newtonian fluid through a circular tube. So, tau is equal to minus mu du dr, that is equal to minus 4 mu u average by into r by r square. So, tau wall, so this minus becomes plus, tau wall